Greetings! Welcome to Electronics 2, lecture number 10. I am Razavi. Today we will continue to look at the differential pair and examine some of its other properties based on what we have seen in the past few lectures. In particular, we will summarize our understanding of differential pairs operation, and then we will delve into the small signal behavior of the circuit, meaning when the difference between the input and the two inputs is relatively small. But before we go there, let's take a look at the lecture from last time and do a quick review of what we learned there. So let's look at this slide here. Okay, so this is where we were last time. We took a bipolar differential pair and assumed that the two inputs are not equal. So we assume that there's a difference between V in 1 and V in 2. So V in 1, for example, is higher than V in 2 or lower. And then what we observed was that if V in 1 is higher, then the tail current prefers to flow more from the left than from the right. So this transistor carries more current, which means node X comes down more because we are drawing a larger current from the resistor on the left. And this transistor carries less current, which means this voltage goes up because we draw less current from this resistor, so we have less voltage drop across this resistor. So generally what we saw was that the two currents of the two transistors have this behavior as a function of V in 1 minus V in 2. If V in 1 minus V in 2 is very positive, meaning this is higher than this, then all the current goes to the left, and we have IC1 at the maximum value, which is the same as the tail current, and vice versa for IC2. Okay, and then we went ahead and derived an equation that shows how Vx minus Vy varies as a function of V in 1 minus V in 2. So the differential output voltage as a function of the differential input voltage. And it came out to be something like this, again, both qualitatively and quantitatively. And we saw that it's a hyperbolic tangent function of V in 1 minus V in 2 divided by 2 Vt. Vt is about 26 millivolts at the room temperature. Okay, so a zero differential input gives us a zero differential output. We can see because with the zero differential input, the two currents are equal, Vx and Vy are equal, the differential output, the difference between the two outputs is zero. Okay, so we are here. And then if V in 1 minus V in 2 is very positive, this argument is a large number, so the hyperbolic tangent of that number would be 1. So we end up with minus RCIEE, which is on this side. And all that means is that Vx is lower than Vy, and that makes sense because V in 1 is high, V in 2 is low, all the currents going this way, So Vx is at the lower amount than Vy. Vy is at VCC. And conversely, when we are over here. We also made a note that if we are in this vicinity, meaning V in 1 minus V in 2 is pretty small, in particular much less than 2 Vt, then I can say that hyperbolic tan of something is equal to that something approximately. So I just replace this whole thing with the argument, and I end up with a simple relationship between Vx minus Vy and V in 1 minus V in 2. So in a sense, we are approximating this curve by just a simple straight line around the origin. And that straight line, as a function of V in 1 minus V in 2, has this much slope. So this is the slope that we saw, right? And we call this the gain also, and today we will elaborate on that more. But generally what we see is that this behavior, which plots the output as a function of the input, for all levels, so it's a large signal model, is nonlinear. You can see that here is linear, but then it gradually begins to saturate, as we call it. So that may or may not be desirable depending on the application. Okay, so let's go back to this slide and see what we can do today. All right, so today we'll just do a quick summary of these properties so that they're all clear in our mind. Summary of diff pair properties. Again, at a high level, without going into details yet. All right, so here are some observations that we made. If V in 1 minus V in 2 absolute value is large, so either V in 1 is much higher than V in 2 or the other way, we see that all of the tail current is steered. This is the expression that we use. Steered, you know, that steering wheel, the steering wheel of your car. So it's steered to the left or steered to the right. So steered to one side. Okay, so if V in 1 is higher, sufficiently higher than V in 2, all the tail currents steer to the left or to the right, depending on if it's the other way around. Okay, so that's one interesting property that we can see, and in some applications we actually utilize this property. So this leads to what we call current steering circuits. We won't talk about this here, but that's one class of circuits that originate from this type of circuit. Okay, the next observation that we also made was if V in 1 is equal to V in 2, so we short these together, and now we allow the common mode level to go up and down, and VCM in, meaning just the DC level of these two, right, goes up and down, goes up and down. We saw that the currents and voltages do not change, right? Because in this case we see that the currents on the two sides are equal, the voltages on the two sides are equal, this current splits equally, so even though the DC level of these two is going up and down, nothing changes. So we articulated this result as the circuit responds to differential inputs. You can see that if the difference between V in 1 and V in 2 changes, the circuit does respond to it, it does something. But it does not respond to the common mode input. If the input common mode goes up and down, the circuit doesn't know. The currents don't change, the voltages do not change. We can also say that the circuit rejects common mode changes at the input. So if the input common mode goes up and down, if these two together go up and down, then the circuit doesn't do anything. But if they go in opposite directions, then the circuit responds to it. Okay, that's the beauty of the differential pair. Okay, all right. And finally, another consideration that we had was that so we saw from the previous page that if V in 1 minus V in 2 is much less than 2VT, so I should have put absolute values on the previous page also, so we are either on the positive side or negative side, but the absolute value is very small. Then we saw that we can approximate the characteristic by a straight line around the origin, and we saw that the slope is equal to minus RC IEE over 2VT. Okay, all right, so these are some of the things that we have discovered so far based on some equations and based on some intuitive understanding. All right, let's now go over a quick example. So here's a quiz that I want to pose to you. Can this circuit amplify? Can this circuit amplify? By amplify, we mean we give it some voltage, some signal, let's say from this microphone, and we measure the output signal. If the output signal amplitude is greater than the input signal amplitude, then we have amplification. So can the circuit amplify? I'll give you 1 minute to think about it. Okay, so what do we have here? Well, given that we know the gain of the circuit is equal to the slope of the input-output characteristic, we can say, well, if the slope is greater than 1, then the gain is greater than 1, which means the output signal is larger in amplitude than the input signal. So, in other words, what we are really looking for is for this whole factor here to be greater than 1, right? So that's the question that we have. And sure, we can set that to be greater than 1. But let me go back to more basic concepts and try to reinforce this, because we will need these results a little later as well. So let's just take it more slowly. Here's our differential pair. And here's V in 1, here's V in 2, RC, and X and Y, okay? And VCC. So, let's assume this. V in 1 and V in 2 are originally equal to each other. Now we allow one of them to go up by some amount, some small amount, and the other one to go down by some small amount. So that represents the signal coming to the circuit. So here's a voltage change of delta V on this side, and a voltage change of minus delta V on this side. Okay, it goes down by delta V, that goes up by delta V. Okay, so they start at the same level. One goes up by delta V, one goes down by delta V. So the total change in V in 1 minus V in 2 is 2 delta V, right? First it's 0, then it's 2 delta V. Okay, so these are small numbers, and I would like to see exactly what the circuit does, right? Of course, we should get the same results, but let's just do it this way. All right, well, I know that this equation holds under all conditions as long as V in 1 and V in 2 are, for example, changing like this, right? There's some difference between them. So what I can say is that Vx minus Vy, the differential output voltage, is equal to minus RC IEE hyperbolic tangent of V in 1 minus V in 2. So it used to be 0 because they were equal, but now they have a difference of 2 delta V. So 2 delta V divided by 2 Vt. And assuming that this 2 delta V is much less than 2 Vt, I can approximate the hyperbolic tangent. So that's approximately equal to minus RC IEE 2 delta V 2 Vt. So not surprisingly, the circuit has amplification if the output voltage change, this, is greater than the input voltage change. The input voltage change was 2 delta V because this went up by delta V, this went down by delta V. In this case, by input, we mean the differential input. So differential input changed by 2 delta V, the differential output changed by this whole thing. So if this whole thing is greater in absolute value than 2 delta V, then we have amplification. So that's what we're going to do. We'll circle this again, just what is like before, and we say this has to be if greater than 1, then we have amplification. Okay, so that's easy enough. All right, so that's just to get comfortable with what's going on in the circuit. And now we will go ahead to the small signal analysis of the circuit. So let me start here. Small signal analysis. So small signal analysis means that the difference applied to the input, so V in 1 minus V in 2, is pretty small. And you might say, we've already done that, right? In fact, yes. Here, we made that assumption and found the slope. Here, again, we made that assumption and we found the gain, right? So it seems redundant to go to small signal analysis. But we will see that this analysis gives us additional tools for analyzing more complex differential amplifiers, differential pairs. Not every differential pair looks as nice and as simple as this, right? There are more complex ones. So in some cases, we do need to be able to perform this small signal analysis on these circuits. Okay, all right. So I do need to go back to Electronics 1 and refresh your memory about two things before we jump into this analysis. So two basic concepts. All right, so A. Remember the concept of transconductance for a single transistor. So here's a bipolar transistor, and the idea is that I have some sort of battery connected to the transistor. The transistor is biased. It has some proper base emitter voltage and some collector current. So let's call this VB, and let's call this IC. Okay, so apply some voltage, you have some current. This voltage is properly secured somewhere, so the device is in the forward active region. Okay, I'm not showing all the circuitry that would be connected here. All right, now I am going to make a small change to the base emitter voltage. So VB will change by some amount, delta V. And as expected, for example, this voltage goes up, this collector current goes up, so there will be a change here. And what we remember is that the ratio of delta IC and delta VBE is the transconductance of the device. So we know that delta IC over delta V is transconductance, right? That's the definition of transconductance. And then we derive this for the bipolar transistor in terms of its bias conditions. So the bias conditions is that it has a collector current, a bias current, let's say 1 milliamp. And we saw that it comes out to be that bias current divided by VT. VT again is KT over Q, 26 millivolts at the room temperature. Okay, so that's one thing we need to remember. The transconductance of a bipolar device is given by its bias current divided by VT. And that's why we bias the transistor. If there's no bias current, transconductance is 0, the transistor is dead. So it's not very good. Okay, the second basic concept is this. The small signal model of the bipolar transistor. So again, just to refresh our memory, it looked like this, right? So here's what we have. The base is on this side. The emitter is here. The collector is here. And I am neglecting the early effect, so there is no output resistance here. Okay, so we call this resistor R pi, and the voltage across it V pi. And we said this transistor acts as a dependent current source, generating a current equal to Gm V pi. Okay, so this is really the same as this, right? The same as this. It just says that if there's a small signal voltage here between base and emitter, which would be this delta V, then I generate a small signal current Gm V pi, which would be this Gm times delta V that we had there. Okay, so let's remember these. Now we go ahead and try to perform a small signal analysis on the bipolar differential pair. All right, I need to go over one more point before we get there. So let's go to the next page and see what we can do here. Okay, so let's go to page number 3. And I will introduce a lemma, okay, an observation. And here's how it goes. If V in 1 and V in 2 change by equal and opposite amounts, so that means they are differential, of course, right? And the change is small, then the tail node voltage does not change. Okay, so let me draw the differential pair again, and I'll show you what this all means. So here's our differential pair. Okay, V in 1, V in 2, RC, RC, X, Y. And the tail node is what we call node P. Okay, so here's what this lemma says. It says that if the inputs change by equal and opposite amounts, so they start at the same level, one goes up, one goes down, so this goes up by delta V, this goes down by delta V, and delta V is small, okay? Provided that these conditions hold, then this voltage does not change. Does not change. All right, so take a moment to understand what we are trying to prove here. This is something we want to prove. And we will see that once we prove this, this is extremely valuable in analyzing differential circuits because it greatly simplifies the analysis. It becomes the analysis really goes back to electronics 1. Okay, all right, so that's what we want to prove, all right? All right, so based on what we just saw on the previous page, so let me go back here and refresh your memory what happened here. Okay, so what we saw was that if I have delta V, positive delta V on this side and negative delta V on this side, then I saw that Vx minus Vy changed by this much. Right, so that's so far so good, right? So Vx minus Vy changed by this much. Okay, so let's go back to page 3, and I'm going to write that again so that we have it available. So what we know is that Vx minus Vy came out to be minus Rc IEE 2 delta V over 2 Vt. Okay, that's what we discovered for a situation like this. All right, so we have seen that this imbalance creates this much imbalance at the output. So this goes up, this goes the other way. Okay, so there's an inversion involved. Okay, so I'm going to work back from here, given that I know the imbalance here, and try to see what happens to this node. Okay, so it's a little complicated. You just have to follow me and see what happens. So we know the change here. We're going to see what happens here. Okay, all right. So if I know the change in these voltages, I should be able to find the change in these currents, right? So IC1 and IC2. Why? Well, because I know that Vx is equal to VCC minus RC IC1. This is VCC, right? And this voltage minus this drop. And similarly this one, so Vy equals VCC minus RC IC2. So if I subtract these from each other, as we saw before, Vx minus Vy is equal to minus RC IC1 minus IC2. Okay, great. So I can write IC1 minus IC2 equals Vx minus Vy over minus RC. So this whole thing divided by minus RC. So that's IEE times delta V over Vt. Okay, nice and simple. So this says that in response to that small differential change that we created here, we also created some difference between IC1 and IC2, of course, right? And that difference is given by this amount. All right, so it's a fraction of the tail current, and that fraction is given by that delta V on each side divided by Vt, assuming that everything is small. All these changes are small. Okay, I would like to find IC1 and IC2 by themselves. So I will also remember that the KCL at this node says that these two currents have to add up to IEE. So IC1 plus IC2 must be IEE. Okay, so we're going to add these up and divide by 2 and all that. We find IC1, right? So that means that IC1 is equal to, we have IEE, and then we have plus, we have IE over 2, and then we have 1 plus delta V over delta Vt. Let me clean this up. So delta V over Vt. Okay, so this gives us the change in the collector current of Q1 as a result of this voltage change that we applied, delta V on this side minus delta V on this side, right? All right, so now let's go and look at this transistor. So let's call it Q1, Q2. Let's focus on this transistor. I have a bipolar transistor, and just isolated, right? It's right here. And it experienced a current change. The current change is given by IE over 2 times delta V over Vt. Right? Before we applied delta V, the current was IE over 2 because each of them had IE over 2. Now that we apply the change it changed by this much. All right, so I have a bipolar transistor, presumably in active region, and its collector current changed by some amount. The question is, what is the change in the base emitter voltage? All right, so we're going backwards. Well, we remember one thing. We remember that GM is the change in the collector current divided by the change in the base emitter voltage. So if I have the change in the collector current and I want to find the change in the base emitter voltage, I say that that's equal to GM times the change in the base emitter voltage, right? Okay, so I have the change in the collector current. Delta IC1 is equal to IEE over 2 VT times delta V. So this bipolar transistor has experienced this much change in its collector current. Therefore, its base emitter voltage must have changed with respect to when V in 1 and V in 2 are equal, right? First they were equal, then they changed. So this base emitter voltage increased to make sure that this collector current increases. And that's the amount that it increased by. Okay, so I am looking for actually delta VBE. So I'm going to write delta VBE1 is equal to delta IC over GM. So that's IEE over 2VT delta V. That is the current change divided by GM. So I need to erase this and make it a little cleaner. Divided by, so that's delta VBE, divided by GM, which is the bias current of this transistor, divided by VT. How much is the bias current? The bias current is half of this, right? Because before we applied the perturbation, this guy had half of IEE and this guy had half of IEE. So the bias current of this transistor before the signal comes in, before this perturbation comes in, is IEE over 2. So IEE over 2VT. Remember, the equation for the transconductance of a bipolar transistor is equal to the bias current divided by VT. The bias current is IE over 2 in this case. Okay, so what happens here? Look at all of this and you see that, well, the base emitter voltage change is just equal to delta V. Okay, so that's a little interesting, a little strange, but let's understand what this means. Okay, so let me change the color of my pen. All right, so let's go back to Q1 and examine it very closely. The base of Q1 went up by delta V. That was how we started the experiment. After we did all of this analysis, we also concluded that the base emitter voltage of Q1 also went up by delta V. Okay, so here's a Q1 in isolation. Node P. This has gone up by delta V, this node with respect to ground. But the base emitter voltage has also gone up by delta V. So then what happens to this voltage with respect to ground? This has to be constant, right? So this is constant. Okay, if you keep this constant and you change this by delta V, this goes up by delta V. And that's what we concluded, right? So that means that if we apply delta V to one side, minus delta V to the other side, and the delta V's are small, the voltage at the tail node P does not change. And we will use that to our advantage when analyzing the small signal behavior. Okay, so let's look at the small signal model, small signal behavior, and see what we need to do. Okay, so the idea is that if I look at the circuit, so I'll draw it again. I don't know how many differential pairs I have drawn in my life a lot, but here's another one. So here's a differential pair, IEE, node P. And we are looking for the small signal behavior of the circuit, meaning that we allow V in 1 and V in 2 to change differentially and by a small amount. So V in 1 and V in 2 change in opposite directions by opposite amounts, or by the same amount in opposite directions, and by small amounts. So very much like what we saw here, right? So V in 1 and V in 2. And under that condition, when we have a differential change at the input and differential change is small, we discovered that this node does not change. Okay? Does not change. So if the voltage at a node does not change with time, what do we call that node in the small signal model? We call it AC ground, right? So this node will be considered AC ground or virtual ground because the voltage does not change with time. So this is AC ground. We call it virtual ground because its voltage does not change with time. The voltage does not change with time because our assumption is that whatever signal is coming to V in 1 and V in 2 is a differential signal and it has a small amplitude. So node P does not change with time. Okay, so if that's the case, and I have these resistors here, in my mind, I can draw it like this, right? I can draw it like this. This is really the small signal model, but I'm sort of blending the small signal model with the transistor symbol as opposed to the small signal model of the transistor. Don't worry, we'll get there, but this is just a simple step in that direction, V in 2. So as far as small signal operation is concerned, not biasing, okay, small signal operation is concerned, these nodes are at ground because we said that this is at AC ground, right? So we say for small signal analysis, we can do this. Analysis. Okay, we can do this. All right, now if you're not comfortable with this, no problem. We're going to go ahead and draw the small signal model of the entire circuit. Okay, so let's go ahead and do that. I need to go to the next page because that's a pretty big circuit. And so here's the actual small signal model. So, all right, so if you remember, for every transistor we have this, right? Every bipolar transistor, we have R pi 1, and this voltage called V pi 1, and this is GM1 V pi 1. That's the transistor on the left, receiving a small signal voltage we call V in 1. Not to be confused with the general V in 1 that we had before. This only signifies the changes in V in. All right, on the other side, so this has a resistor, RC, that goes to AC ground. And similarly on this side, we have RC, and then we have this current, which would be GM2 V pi 2, and then this R pi 2 with V pi 2 across it, receiving V in 2, and then these two sources are connected and they go to the tail current source. The tail current source is constant with time, so, and it's independent. So when we replace it with a small signal model, it becomes an open circuit, so it's gone. There's nothing here. Okay, it's not shorted to ground, it's open. All right. But I know one thing. Remember we said that as long as these two are small and differential, this node voltage does not change with time. If the voltage at this node does not change with time, it's AC ground. So I'm going to ground it. Okay, this is because it's an AC ground, and that's because V in 1 and V in 2 are differential voltages and small. Okay, so when I ground this point, what happens? I see that the circuit actually breaks into two halves. One half here with this emitter grounded, one half here with this emitter grounded. And that's reminiscent of what we saw on this page. You see? One half with this emitter grounded, one half with that emitter grounded. So for small signals that are differential coming to the circuit, we can envision the circuit as two halves that are pretty independent, right? Because their emitters are not connected to each other anymore. They're just grounded, right? There's no interaction between this part of the circuit and this part of the circuit. So now that we have managed to do that, the circuit actually reduces to what we know from Electronics 1. This circuit here, right? This is a circuit we know, and this is another circuit we know. Each of these is just a common emitter stage, so its voltage gain can be readily written from what we remember from Electronics 1. Okay, so let's go back to this page and write that out. So this is node X, this is node Y. So again, I have this half of the circuit and this half of the circuit, right? So we call these half circuits. Okay, each of them. So let's draw only one of them. Again, I go back and forth between this drawing of the circuit and that drawing, okay? Just keep in mind that we're dealing with small signals. So this is RC, this is node X, this is Q1. This is what we call a half circuit because we saw that for small differential inputs, once this node is AC grounded, these two are separate now. This has its own ground, this has its own ground, so I can analyze them separately. Okay, so what is the voltage gain from here to here? We know that the voltage gain is minus Gm of the transistor times the load resistor, provided that we neglect the early effect. Okay, so that means that I can say Vx equals minus Gm RC V in 1. How about the other side? Same story. So I can write Vy equals minus Gm RC V in 2. All right, so I'm interested in the differential output voltage. So Vx minus Vy equals minus Gm RC times V in 1 minus V in 2. So it makes sense to call this the voltage gain of the circuit. Why? Because in response to a differential small signal input, we got a differential output. So this divided by this would give us the gain. So that's what we call the differential gain. AV is equal to Vx minus Vy over V in 1 minus V in 2, and that's just minus Gm RC. So this is called the differential gain or voltage gain. Okay? So this is very simple and beautiful, right? We saw that this equation actually was the voltage gain of a simple common emitter stage in Electronics 1 as well. So it just happens to be the same for a differential pair. So in this case, we are interested in the differential output, so Vx minus Vy divided by differential input. That's the gain that we define. So for example, the signal coming to these two is somehow differential. So if it's a single under signal from this microphone, it goes through some circuitry, maybe a transformer, as I showed you before, becomes differential, arrives here, is amplified by the circuit, and then it's produced at x and y. And when we measure Vx minus Vy, we see that we have gain, and the gain is given by this much. So if that gain is reasonable, then it's a reasonable amplifier, right? So indeed, the differential pair can act as an amplifier from this perspective also. Okay, that is the small signal analysis of the circuit. And just to get things straight, let's also remember that Gm for each of these transistors is equal to its bias current, which is half of the tail current, right? So IEE over 2 and then over VT. So if I plug that in here, it comes out to be minus RC IEE over 2VT. Right? So IE is just a constant value. RC is constant, VT is constant. That's the voltage gain of the circuit. And we derived this a number of times in the past, right? So if I go back here, you remember that over here we found that the slope is given by this, the slope of the large signal characteristic. And then again, we found the response to a small voltage change, and again, it was the same amount. And now, using a formal small signal analysis, we saw the same result. So the voltage gain is given by this much. So by proper choice of RC, the load resistors, IEE, the tail current, we can obtain a certain amount of gain that we are looking for. Maybe a gain of 5, maybe a gain of 10, something like that. Right? So that's how we build an amplifier out of a differential pair. Of course, in all of this, the assumption is that the input differential signal is small and it's differential. So one side goes up, one side goes down, so that these approximations are valid. In particular, this approximation that this node does not change with time is valid. Okay. Our time is up. Next time we will expand upon these ideas and develop a better understanding of the differential pair. I will see you next time.